Hi there, Mr. Sutton here with the Pre-Cal Honors 3-6 Extra Practice Number 1 solutions on features of rational functions. For this one, we're trying to find intercepts, asymptotes, and holes for this rational function. It looks like we might be able to factor this, so that's probably a good idea to start things off, just to see kind of what the common factors are and what the zeros are of the numerator and denominator. So up top, we need numbers that multiply to negative 18 and add up to positive 7. Negative 2 and positive 9 will do the job up there. Down below, we need to multiply to negative 10 and add up to 3. So if we have negative 2 and positive 5 with my x's in parentheses, that'll do it. And we see here that the x minus 2's can cancel. So that's going to leave us with a simplified function of x plus 9 over x plus 5. Now, going through each of the features, let's do the intercepts first. X-intercepts, that will be things that zero out the simplified numerator. We don't want any things that make the denominator 0 to count as x-intercepts, but this x plus 9 seems harmless enough. So we set x plus 9 equal to 0 and solve, giving us an x-intercept of negative 9. 2 would have been an x-intercept, but it also makes the denominator 0, so the function doesn't exist there. And that's why we did that in the beginning, to catch that kind of stuff. Now for the y-intercepts, we're going to plug in 0 for all the x's and see what happens. So plugging in 0 in the original function here for all the x's, all that's left over when you do this is negative 18 over negative 10, which we can reduce to 9 over 5. Next, for vertical asymptotes, that's going to be whatever zeroes out the simplified denominator. It's an undefined we can't get rid of. This x plus 5, if we make that 0, that's going to give us a vertical asymptote. So x equals negative 5 is our vertical asymptote. Now for holes, those are things that would have made the function undefined but could be canceled out. They're removable. So this x minus 2, if we zero that out, the x value where that becomes 0 is going to be our hole. So x equals 2. And there's a y value you could find if you wanted to plug this back in to the simplified function here. It would have actually been 11 over 7. But anyway, the horizontal asymptote, taking a look at the degrees of the original function, we see that the highest is x squared in the top and bottom, so these are the same degree, numerator and denominator. That means the horizontal asymptote is just going to be the ratio of our lead coefficients. So the 1 and the 1, the invisible ones next to the x squareds, give us our horizontal asymptote of 1 over 1, or just simply 1. For this one, we're trying to find intercepts, asymptotes, and holes for this rational function. So to start things off here, I think I'm going to factor this because I don't really know what I'm dealing with otherwise. So in the numerator, we're going to be looking for, this is a little bit tricky here, we're going to need factors of 3 and factors of 5x squared. Now, those are both prime numbers, so there's only so many different combinations we can try. We need a 1 and a 3 in our parentheses, and we're also going to need a 5x and an x, and something's got to be negative. So let me try out one such combination, 1 minus 5x and 3 plus x. Let's see if this works. So I have negative 5x times 3, that's negative 15x. We have a 1 and an x giving me a 1x. So that adds up to negative 14x in the middle, which is what I'm looking for. Let me move down to this one here now. So I know I need a 1 and a 3 to get this 3, and an x and a 2x to get this x, and thankfully they're both going to be positive. So let me try this combination. We have a 1 and plus 2x and a 3 and an x. So if I do 2x times 3, that's 6x. 1 times x is x, and that adds up to 7x. Hey, I got it on the first try. How about that? So one thing I do notice is that these 3 plus x's cancel out. So we're really left with 1 minus 5x over 1 plus 2x. Now that we've factored this and simplified a bit, let's go through and analyze the different features of this rational function. We'll start with the x-intercepts. For those, we have to make the simplified numerator 0 to zero out the whole fraction, because on the x-axis, the y value, the output is 0. So we have 1 minus 5x equals 0. And if I just add 5x to the other side and divide by 5, I've got 1/5 for my x-intercept. For the y-intercept, I need to plug in 0 to all of the x's in the original equation here, the original function. So if I do that, so zeros for all those x's in the original, everything is going to zero out except for this 3 and this other 3, which we can reduce to 1. Next, let's do the vertical asymptotes. So that's going to be whatever zeroes out the simplified denominator. So this 1 plus 2x, let's see what that equals. Let's see what x equals if that's 0. So if I subtract 1 and divide by 2, that's negative 1/2 for the vertical asymptote. For the wholes, that's going to be whatever zeroes out any factors that got canceled out, like this 3 plus x. So if we see what makes 3 plus x equal to 0, that's going to be a whole at negative 3. And then finally, the horizontal asymptote, since we have the same degree for the numerator and denominator, they're both second degree, our horizontal asymptote is going to be the ratio of the lead coefficients, or at least the highest degree coefficients. So we're going to have negative 5 over positive 2 for this one. For this one, to find intercepts, asymptotes, and wholes, we want to first factor this expression here, just to see if there are any common factors that we can cancel, and that'll also help us solve for zeros in the numerator and denominator. So for our denominator, we can definitely factor a 4 out of everything, leaving us with x squared plus 3x minus 4. And then we can factor this a little bit further, numbers that multiply to negative 4 and add up to 3. That would be negative 1 and positive 4. So we see that we actually do have a common factor of x minus 1 that we can cancel, and that leaves us with just 1 over 4 parentheses x minus 4. All right, so let's go through now and analyze this and figure out all these different attributes. So for x-intercepts, we need to take the simplified numerator and set it equal to 0 to see if there's anything that zeroes out the fraction. And we see that when we do that, 1 actually does not equal 0. So there are no intercepts. If there's no variable upstairs, there's no way to make the fraction 0, unless the thing upstairs is 0, but it's not. So no x-intercepts. So we move on to y-intercepts. For that, we try to zero out the original function here, or at least we try to plug 0 in for the x's in the original function. So we got 0 minus 1, and 0 for all these other x's. And when we do that, all that we're left with after things zero out is a negative 1 in the numerator, a negative 16 in the denominator, so that's a positive 1 over 16 for the y-intercept. Now for vertical asymptotes, we set the simplified denominator equal to 0 to see if anything makes the simplified fraction undefined. So we have 4 parentheses x plus 4 equals 0. So x plus 4 then must equal 0. So then x equals negative 4 is our vertical asymptote. Next, for wholes. These are going to be factors that got canceled out and otherwise would have given you 0 in the numerator and denominator. So this x minus 1, if we set that equal to 0 and solve it, we'll get the x value of the whole. In this case, that's x equals 1. And then finally, for the horizontal asymptote, looking at the original expression, we see that we have a bottom-heavy fraction. The x squared is a higher degree than the x up here. So since we are bottom-heavy, we automatically have a horizontal asymptote of y equals 0. To figure out features of this rational function, we're going to first try to factor things and simplify the fraction. So in the numerator, it looks like I have a common factor of x that I can take out, leaving me with x plus 3. In the denominator, I have factors of negative 6 that add up to the 1 in the middle here. That would be negative 2, positive 3. So x minus 2, x plus 3 would be what we're looking for. And we see that, lo and behold, the x plus 3s are going to cancel. So that leaves us with x over x minus 2. So let's go ahead now and analyze this thing to see what our intercepts and asymptotes are. For x-intercepts, we are setting the numerator, the simplified numerator, equal to 0. In this case, all that's left is x, so we literally just say x equals 0, and x equals 0 is the x-intercept. We have an intercept at the x value 0. Let's do y-intercepts now. Now, if you're clever about this and you realize that the x-intercept of 0 is the origin, you might also realize that that's a y value of 0, and so we have a y-intercept of 0. But you could plug 0 in to the entire function, just like I did here, and that also works. So if you do that, we notice that we have 0 in the numerator, negative 6 in the denominator, so 0 over something that's not 0 is automatically 0. All right, moving on to vertical asymptotes. Those are going to be factors in the numerator, or rather the denominator, that were not canceled out, setting those equal to 0, things that zero out the simplified fraction. So we can say x minus 2 equals 0 for that, and if x equals 2, then the simplified fraction is undefined. It's an unremovable undefined. So x equals 2 is a vertical asymptote. For wholes, we look at things that would have zeroed out the denominator but got canceled out, so they're not as bad as vertical asymptotes. In this case, x plus 3 falls into that category. So if I set that equal to 0, I see that x equals negative 3 is the x value of a whole. Finally, for horizontal asymptotes, we look at the degree of the original function, the original fraction, and we see that we have the same degree, both x squareds, both second degree, in the numerator and denominator. Since it's the same degree, we just take the coefficients of the highest terms, which is an invisible 1 and 1 in this case, take a look at the ratio of that, and simplify it. So in this case, 1 over 1 just equals 1, so y equals 1 is the horizontal asymptote. For this problem, I'm trying to analyze the features of this rational function. This one's a little bit crazy. Let's go ahead and see how much we can factor and simplify this before we start taking a look at intercepts and asymptotes and wholes. So first I'm going to start by just rewriting the denominator. I know I can factor that, but I've got a little bit of work to do in my numerator first. So up top, trying to factor this, I see that I have 4 terms, and the ratio of coefficients of the first 2 terms, 1 and 1, is the same as the ratio of the coefficients of the second terms, also 1 and 1. This tells me that I can use factoring by grouping. So let me take a common factor out of both the first 2 and the last 2 terms. For the first 2 terms, I can take out an x squared, which leaves me with an x plus 1. For the last 2 terms, the only thing I can take out is a 1, but that's okay. Still leaves me with an x plus 1. That's okay, though, because that's the same thing that I ended up with for those first 2 terms. So now moving forward here, I can factor an x plus 1 out of all of that, and that leaves me with an x squared plus 1 in my other parentheses. Now down below here, I need numbers that multiply to 1 and add up to 2. That would just be 1 and 1. So I could write x plus 1 squared, but I'm actually going to write it twice just because it's easier to see then when I cancel out these x plus 1s. It's easier to see what's left over here. All right, so let me go ahead and analyze my intercepts and all the rest of it. For x-intercepts, we need to set the simplified numerator, x squared plus 1, equal to 0 to see what zeroes out the whole fraction. Now, in this case, just looking ahead, if I subtract 1 and then square root, I'm going to get some imaginary numbers. So there are actually no x-intercepts because they have to be real numbers to be on the x-axis. Moving on to y-intercepts, if I plug 0 into the original function here, so zeros in all those different x's, that's 5 different zeros that I'm plugging in all over the place, that zeroes out everything except for the 1 and the 1 here, which if I reduce 1 over 1 leaves me with just 1 for the y-intercept. Now for vertical asymptotes, I'm taking a look at things that zero out factors in the denominator that did not get canceled out. So an x plus 1 got canceled out, so you might be wondering, well, do I have a whole being caused by that? But this is kind of an interesting problem because there's an x plus 1 that did not get zeroed out, or canceled out, I should say. But we can zero it out. If I set this x plus 1 equal to 0 and I solve, I see that negative 1 is going to actually make the simplified fraction undefined. So that ends up being a vertical asymptote. So that answers the question then of whether we have a whole at negative 1. We don't. There's no whole there because even though this x plus 1 got canceled, there's still one that we couldn't get rid of. So negative 1 ends up being worse than a whole. Now for horizontal asymptotes, we're looking at the degree of the original function. We see that we have a top-heavy function here. X cubed is a higher degree than x squared. So that means we have no horizontal asymptote. But we do have a slant asymptote that we can now find. To find that, we basically have to divide the numerator by the denominator. And for this, I'm going to go ahead and use this simplified version, x squared plus 1 over x plus 1. Now, since I'm dividing by a binomial here, not just x, but x plus 1, I can't just divide everything by x. I actually have to use a little synthetic division here. So let me write the coefficients of my numerator, which is 1 for the x squared, 0 for the missing x term, and 1 for this constant of 1. And my box number is going to be -1 because that zeroes out the denominator that I'm dividing by. So -1 is my box number. Bringing down that first one, 1 times -1 gives me -1, plus 0 is -1, and it doesn't really matter for the remainder here, but let's just finish it. -1 times -1 is 2, or 1 rather, 1 plus 1 is 2. There we go. So we end up then with just looking at the coefficients of my quotient here. My quotient is going to be my slant asymptote, and that is going to be the line y equals 1x minus 1.